Let me introduce to you the self-adjoint and Hermitian operators. And I have to say in advance that I'm not talking about the mathematically rigorous kind of definition, but I will be giving you a more loose version where physicists use. Let's say we have a vector space V with the inner product. When I say vector space, it's good to have in your mind some examples, like say if you have 1, 2, -1 as a vector, another 3, 1, 1 as a vector, and these are all in R3. So if you think about R3 as a vector space, then you can do a dot product or this inner product. I'm using this notation for a general inner product, but in this context, dot product is the inner product. And 1 times 3, 2 times 1, -1 times 1. You add these things. That's how you compute a dot product, right? So think of this as an example when you think about a vector space with an inner product. Now, let's say A is a linear function from V to V. In other words, you have a vector U in V, and A of U would again be in V. So A is a function from V to V, and being linear means that if you have two vectors U and V, then C1, C2, if C1, C2 are scalars, this is same as C1AU plus C2AV. Now, when you have a vector space with an inner product and a linear function, the adjoint of A, which is usually denoted as A star, is another function from V to V that satisfies this following equation. AUV is same as UA star V. If this is true, in other words, no matter what kind of vectors you feed in, if this one and this one is same for another function, another linear function A star, then you say A star is the adjoint of A. In other words, adjoint allows you to move one operator to the another slot. Now, there are some cases where AUV and UAV is the same. In other words, A actually satisfies the equation for being an adjoint. Another way to say this would be to say that A and A star are the same. The adjoint of A and A is same. In that case, you say A is a self-adjoint operator. Okay, you say A is self-adjoint, and you have to. This is the warning I wanted to say. In functional analysis of mathematics, where they deal with infinite dimensional vector spaces, where the vector spaces are usually function spaces, there the notion of self-adjoint has to do with the domain of A being complete or boundedness. And this is much more involved, so I do not intend to explain this one. Alright, so let's think about some examples. For finite dimensional spaces, matrices can be used to represent any linear function. So, for example, if you think about R2 as a column vector, so two numbers, 3, 1, and say you have this number here, you can add two column vectors and you get a number. So it's possible to think about R2 as a column vector with addition as usual, matrix addition, and scalar multiplication as something like this. If you have a 2, 1, and 3 as a scalar in front, you can multiply it as 6, 3, like that. Well, so you can think of column vector spaces as vector spaces on this space. Things like 1, 2, 4, 3, a matrix like this, can take the role of a linear function. So suppose you had 3, 1 here, then 1 times 3 will be 3. Well, you multiply matrices this way, right? So 1, 3, 2, 1, so that's 5. And 4, 3, 3, 1. 4 times 3, 3 times 1, so that's 15. So that gives you a result, and you can check that this is indeed a linear function. Now, if this dot product is the usual dot product, say if you have 3, 1, 2, -5, and if you do a dot product between them, how do you do that? 3 times 2 is 6, 1 times -5 is -5, so you get 1 as your result. Well, this is same as multiplying 3, 1 matrix with a 2, -5, right? Because matrix multiplication does this, 3 times 2, 1 times -5, so that's exactly 1. That means you can represent any vector dot product, any dot product here, as take the transpose of the first one and do a matrix multiplication to the second one. Now in this dot product, you can see that the adjoint is like the transpose. Let me explain why. So think about this equation here. What is AUV? Well, according to our definition, it should be AU transpose times V, right? But then further, this is same as U transpose A transpose V. Oh, that's because you have a property of transpose that says AB transpose is the same as B transpose A transpose. And therefore, if you have if you apply that to write it like that, then you can see that once you think about this as some W, this looks like UTW, and that is exactly the same as taking U and W and taking the inner product. But what was W? W is UATW, so that tells us that over real numbers, the adjoint of a matrix is same as its transpose. So we did this calculation and we see that the adjoint of a matrix is transpose. Alright, so what's the implication then? That means that self-adjoint matrices are matrices that satisfy A equals to AT. In other words, if you have a matrix A, and if its transpose is same as the original, it's self-adjoint. But what does that mean? If you take the transpose, the diagonals stay the same, but whatever that's in here goes to the other side. Whatever that goes in here goes to that side. So that means if you have A equals to AT, that's a symmetric matrix with respect to this diagonal. Okay? So for matrices, it means that self-adjoint is same as symmetric. Now, when it comes to infinite vector spaces, we talked about function spaces. Like function spaces, something like L2 space. In that case, there are two important operators that are self-adjoint. One is called the Laplacian. So think about these functions that are second differentiable. So I guess usually they write it as like C2 and over some, let's say R3. Okay. So you have three variable functions that are second differentiable, and on here the Laplacian operator, which is you differentiate twice in the x direction, differentiate twice in the y direction, differentiate twice in the z direction, and you add them up. That happens to be self-adjoint. Okay. The physical meaning of this operator is explained in some other videos of mine, so I want you to look at divergence, curl, and Laplacian video for that one. And this happens to be self-adjoint. In other words, on R3, let's say you define an inner product of two functions as you multiply them and you integrate over this R3. And with this inner product, this satisfies all the axioms for inner products. And over here you have this property that Laplacian of G, F, is same as G Laplacian of F. Now I'm being very intuitive and not rigorous here, because this is really, if you write it out like that, you'll see that what I'm writing here is a multivariable version of integration by parts, because one derivative goes to the other, or you can say it's like the Green's identity. And when you do that, the boundary terms appear, and you really need some conditions than this one. So you have to say that G and F decays to 0 fast enough as x and y and z goes to infinity. But you get the idea. With certain boundary, so I would say with some condition here, this operator with certain boundary condition is self-adjoint. Okay? And this operator happens to come up in, say, heat equation, Laplace equation, Poisson equation, in Navier-Stokes, in electromagnetics, so even quantum mechanics. So this operator is everywhere. So having a self-adjoint operator appearing in so many different contexts, that tells us that studying self-adjoint operators are really important. Now, the second example of a self-adjoint operator appearing in function spaces is the multiplication operator. It's an operator that just multiplies some function. Let me give you an example. Let's say you have a function, and this operator A is a multiplication operator. What it does is it multiplies this given function by some other function. So let's just say multiplication by x. Now this is easily seen to be self-adjoint because think about the following. If you have AFX and GX and you want to take the inner product of them, then we agreed that the inner product looks like just multiplication of those two functions, dv over R3. And since AF, we decided that's multiplication by x, and since we are allowed to replace the integrand with an algebraically equivalent thing, well, multiplication is commutative, so I can move the x over here and write it as fx times x times g of x. But what is this? This is same as f ag, right? So we see that a can be moved from here to there, therefore it's self-adjoint. Now, multiplication operator being self-adjoint is another important fact, and in quantum mechanics, a lot of times you're going to see this Laplacian operator and multiplication operator working together. The Schrödinger equation, which is very important in quantum physics, it has the form of IH bar. This is some constant, and I is the imaginary number, and then you take the partial with respect to t equals to negative h bar squared over 2, and then Laplacian of phi plus, for the case of harmonic oscillator, this is like x squared plus y squared plus z squared psi. Okay, so this is a multiplication operator acting on phi. This is the Laplace operator acting on phi. So you can see that this entire right side has this operator L, which can be defined as squared over 2 Laplacian plus x squared plus y squared plus z squared. This being applied to phi, and this, since this is self-adjoint and this is also self-adjoint, this is really self-adjoint. Now, I've been talking about self-adjoint only in the real vector spaces, and when you go to complex vector spaces, you have to modify the inner product slightly. So if we allow these f and g to be complex, then the inner product has to have this bar on one of them, and in that case we have something called the Hermitian rather than self-adjoint. So in the literature you'll see that this operator here is what people call the Hamiltonian operator, and it's always Hermitian. Alright, speaking of complex vector spaces, let's talk about complex vector spaces and Hermitian. So if you have a complex finite dimensional vector space, the inner product will have this bar there, okay? So if I have, say, 1 plus I, and then 2 dotted with, say, 1 and 2 minus I, then the dot product is not the one that you're accustomed to seeing. It's supposed to have this bar on the second one. So 2 times 2 minus I, bar. Now, bar operator doesn't do anything on the real, so when U and V are real vector spaces, this bar doesn't do anything, and you recover the usual dot product that you know. But when it comes to complex vector spaces, having the bar allows the dot product to have some property which is positive, being a positive bilinear operator. So it's not bilinear, it's sesquilinear. It becomes positive, and in other words, what I'm trying to say is that in one dimension, one complex variable, you can think of this as a vector space, then the norm of a complex number is defined as square root of z times z bar. And if you define dot products this way, then even in many dimensional complex vector spaces, you can say the norm of a vector is same as v dot v bar. Okay, and this v dot v bar is what we call the inner product. So this inner product of v with itself, this formula that we like to use still works if you include this bar. That's why we have this bar. All right. For this inner product, you can see that the adjoint will require this bar in there. So if we do the calculation again, since we have this as AV transpose times W bar, this is same as V transpose A transpose W bar, and that's V transpose A transpose W bar of bar. See, the trick is that anything is bar. So if you complex conjugate twice, you return to the original thing. So this is same as the original. All right, so you have this, and you can rewrite this as VT AT bar W, and therefore the adjoint in the complex context, adjoint is AT bar. And whenever this is true, whenever A is itself is same as its adjoint, then we call it Hermitian matrices. So to distinguish this adjoint from the other one, we sometimes call this as Hermitian adjoint. And if any matrix is same as its Hermitian adjoint, then we call it Hermitian matrices. Notice that if A itself only has real values in there, so if A is a matrix with only real elements in there, then this bar doesn't do anything. So you can say that any real adjoint matrices are, again, Hermitian matrices. So that's why we sometimes call some operator self-adjoint, and sometimes we call it as